You know, recursion, it can feel a little bit like magic, right? Where a function somehow just knows how to solve a problem by calling itself. But let's be honest, it can also be super confusing. If you've ever found yourself wondering how it all works without just getting stuck in a crazy infinite loop, well, you're in the right place. It all really comes down to one big question.
Yeah, so that's the big mystery, isn't it? How on earth does a function pause what it's doing, call a fresh copy of itself, wait for an answer, and then pick up exactly where it left off? It sounds almost impossible, but it's all handled by this really elegant and surprisingly simple system that's working behind the scenes.
So here's what we're going to cover. We're going to pull back the curtain and look at Recursion's secret weapon. Then we'll get properly introduced to its manager, the call stack. We're going to follow a function step by step on its journey down the rabbit hole, and then watch it climb all the way back up with the answer. We'll also look at what happens when things go horribly wrong, and we'll wrap up with how you can really master this powerful concept.
All right, so what's the secret sauce here? What is this hidden engine that's making the whole thing run and keeping track of all the moving parts?
Well, the whole secret. It's something called the call stack. Now, this is a really fundamental piece of how pretty much all modern programming languages run. And once you get how it works, all the magic of recursion just melts away and becomes this clear, logical tool that you can actually control.
So, let's get formally introduced to this unsung hero of our code. The best way to think about the call stack is like an air traffic controller for your functions. It's managing every single takeoff and landing, which, as you can imagine, is absolutely critical when you're dealing with the complex flight path of recursion. Okay, so what is it really? At its core, the call stack is just a structure in your computer's memory that's keeping a list of all the functions that are currently active. But the key principle here, the thing that makes it all work, is last in, first out, or LIFO. So what does that actually mean? Think about it like this. Say you're washing a stack of dirty plates. You put the first plate down. Then your friend gives you another one, and you put that right on top of the first one. Now, you can't get to that bottom plate until you wash the one on top, right? The last plate you put on the stack is the first one you have to take off. The call stack works in exactly the same way, but with function calls instead of plates. So each one of those plates we just talked about, in programming, that's called a stack frame. Every single time a function gets called, a brand new frame is created and pushed onto the top of the stack. And this frame is like a little private office for that one specific function call. It holds everything it needs, the inputs it was given, any variables it creates for itself, and this part is so important, the return address, which is just a note on where to go back to when its job is done. This little private office is what lets each recursive call do its own thing without getting confused by all the others. Okay, enough theory. Let's actually see how this whole thing works. We're going to trace a real classic, the factorial function. We'll follow factorial of 3, which should give us 3 times 2 times 1. Okay, so here's where it all kicks off. Our program calls factorial 3. Right away, a stack frame for this call gets pushed onto our, for now, empty call stack. Inside this frame, the value for its parameter n is 3. So far, so good. The stack has one frame. But here's where it gets interesting. Inside the code for factorial of 3, it realizes it needs the answer to factorial of 2 to do its job. So the factorial of 3 function is paused, and a totally new stack frame for factorial of 2 is pushed right on top of the stack. See how factorial of 3 is still there? It's just waiting, patiently underneath. And that right there, that's the whole game. Every single time the function calls itself, another layer, another stack frame gets added on top. And each one has its own private workspace. See? The n in the top frame is 2, but the n in the frame just below it is still 3. They're completely separate. And you guessed it, this just keeps going. Factorial of 2 calls factorial of 1, which then calls factorial of 0. The stack gets taller and taller until, finally, we hit our base case. The base case is just the stop sign. It's the condition that tells the recursion, okay, you're done, stop calling yourself. For our factorial function, that's when n hits 0. This is the deepest we're going to go. All right, we've gone all the way down. But now for the really cool part, the climb back up. This is where the stack starts to unwind, and we actually figure out the answer. That function right at the tippy top of the stack, factorial of 0, it doesn't make any more calls. It knows the answer is just 1, so it returns that value and its job is done. Poof, its stack frame gets removed or popped right off the top of the stack. And what do we see now? It's the factorial of 1 frame, which has just been sitting there, waiting this whole time. It was paused, waiting for the result from factorial of 0. Well, now it has it. It gets that value of 1.
does its own calculation, which is 1 times 1, and now it's ready to return its own answer.
This is absolutely crucial to understand. As one frame gets popped off, it basically leaves its return value behind like a little gift for the function just below it. It's like passing a baton in a relay race, except you're going backwards, up the stack.
And this beautiful little cascade just continues. Factorial of 1 returns 1, and its frame is popped. Factorial of 2 grabs that 1, calculates 2 times 1 is 2, returns, and it gets popped. And finally, we're right back where we started, at our original factorial 3 call. It gets to 2 from the previous call, calculates 3 times 2 is 6, and returns the final answer. The stack is empty again, and our problem is solved. Pretty cool, right?
Okay, so that's when everything goes right. But what happens if we mess up? What if we forget to give our function that all-important stop sign?
See, a healthy recursive function always has a defined base case, an exit strategy. The stack builds up, does its thing, and then nicely unwinds. But if you forget the base case or you write it in a way that it can never be reached, the function just keeps calling itself forever. It pushes frame after frame after frame onto the stack, which just grows and grows and grows until it literally runs out of space. And that's when your program crashes with that infamous error, Stack Overflow.
So why does all this matter? Well, getting a feel for the call stack isn't just some academic exercise. It's a really practical tool that will help you write much better and much safer recursive code.
So here's what you absolutely have to burn into your brain. First, recursion isn't free. Every single one of those calls eats up a little bit of memory for its stack frame, which means really deep recursion can actually be a big problem. But the number one thing, the main cause of all the pain, is a missing or just plain wrong base case. So if you only take one thing away from this, it's this. Always double check that your function has a clear and guaranteed way to stop.
So there you have it. By pulling back the curtain and actually visualizing the call stack, recursion isn't magic anymore, is it? It's a predictable mechanism. You understand the engine, you understand the costs, and you understand the dangers. The magic is gone, but what you have now is a solid understanding. And that leaves us with a much more interesting question. Knowing how it really works, when should you actually choose this elegant but sometimes dangerous tool for your own code? Well, that's the next step on your journey.